Okay, so we talked about the forces, but we didn't talk what is actually the fields, right? What produce these fields? So what produce electric field?
Charger?
Exactly. If I have charge, this is a charge. So this charge gonna actually produce an electric field going that direction, right? And if I have a negative charge, so the other way around. So it's gonna produce this kind of electric field. So we have an equation that actually tells us what is the electric field. This is called Coulomb's law, right? Good. So Coulomb's law is going that way. It's going that way. D, let's do it here. You know what? So this is what produce charges, right? Electric field. Right? So it's actually dE, a small contribution of electric field, is due to some experimental constant, Ke, okay? dQ, right? Some contribution of charge. This is a charge, right? Multiply by the direction, right? RdE, let's call it, divided by RdE squared. Good. What produce magnetic field? Moving charge. Okay, so this was electric. So if I'm gonna have charge that actually moves according to the right hand rule, the magnetic field is gonna be like this. Remember? That's what's going on. So what is a moving charge?
Current.
It's a current. Okay? So we have the same concept here. Okay? This is how to find the field. The field. Good. So we have the same thing here. This called Coulomb's law, and this called biu-Svar, right? And it say the same thing. You have a constant Kb, okay, and you have the current I. I is I equal dq to dt, right? Multiply by the vector dl. dl is the distance that this particle actually travel in the direction of the current, right? So it's actually, let's do it even simpler. This is dq, and it's gain some velocity. So velocity is dl divided by dt. This is dq. So this is I dl, right? That's what we really care about. That's the reason we have here I dl. Good. And this now have a cross. Remember that the magnetic field have this cross term, which it's kind of a little bit hard. RdB, which is the direction, right? Divided by RdB squared, magnitude, right? So if you need to find magnetic field or electric field, that's what you should do, okay? And I want you to remember, like we have plus that actually tell us what is the direction outward, right? And minus tell us the direction of the electric field is inward, right? The same thing we know about the magnetic field. The parallel idea is the right hand rule, okay? It's the same concept. Good. So let's do a biu-Svar question, and I just want to remind you that in the class we saw this constant as mu fs divided by 4 pi, and this term is also a 1 over 4 pi epsilon, right? So it's depend on the end solution that you see in the exam to pick which one to use. Kb, Ke, epsilon, mu, okay? It's just a constant from experiments. Good. So let's do a biu-Svar question. So I think this question that I have here, it's the most repeatable question ever in exams. Seriously. Okay? So the question is from 11 winter B12, it also appeared on 11 winter not here, also appear on 10 SA4, spring A4. It's also the same one appear on spring on 15 SB12. 3 different exams, the same question, okay? But I think it's a really good question, okay? So let's use this question. So the question is going that way. There's a wire with the current 2I. Why 2I and not I? Because the current's going to split, okay? Just for that. So the current's actually going to split to two different wires. This one here, hop, and this one here, hop. This one here. Let's do it in different color, blue. This is black. Two different wires, right? And going back to be 2I here. Good. So to this current I'm going to call I1, and to this current I'm going to call I2. Okay, gotcha? Good. Okay, so now what I want to ask you is, what is the magnetic field here? Be in, okay, in the middle, okay? Good. I see people in the audience starting doing that, that's good, okay? So here nobody talks about mass. Mass is not given, so probably forces not gonna help us, but they ask us about the magnetic field. So magnetic field probably gonna be this equation, biu-Savart equation. Good. So how we can solve it? So I'm gonna write down biu-Savart equation. So biu-Savart equations say that each chunk of a current, for example, this chunk of current, actually gonna contribute to me this constant KB, right? I cross, I multiplied by DL cross RdB direction divided by the size RdB squared, right? So every time you see this biu-Savart term, the only thing that need to be of your concern is to find out two vectors. This one and this one. That's all you need to do. This probably gonna be easy / given, okay? The thing in this question is that I'm gonna be a little bit problematic. Why? Look at the question. What is the difference between here and here? So let's talk about it. So what is RdB? What is the definition of RdB? Do you remember it? It's a distance, right? This is easy one. But RdB is actually the distance from the source, the one that produced the field, positive charge for electric field, and for magnetic field it's the current, right? The one that produce it to the direction of the center. So in our case this is given to be A, some size, so this is easy. But what is the direction? Minus the radian, okay? And this is hold for both of the wires, right? I'm going to give you a little bit what's going on. We need to find the magnetic field in the center, right? This is the question. That's what is given, okay? And we know that each piece of current actually contributes some magnitude here, okay? Good. So I told you that we're going to use biu-Savart. And in order to use biu-Savart, I need to understand what are these two vectors, okay? What is DL? What is DL? What is size of DL? Small piece of wire here is, if the radius is given A, we can use the radians, right? And say, okay, this is easy. This is A d theta, right? The radius multiplied by small angle. This is going to give us immediately this. But what is the direction of it?
Radial.
Radial is this, in and out. But you are doing the tangential one, right? The tangent one. But look, we have a problem. Why we have a problem? Because the current's going in this direction up, which means negative theta. You see it? If theta rising to this direction, this is the negative one. So this is for 1, and this is, the plus is actually for 2. So I already see that I need to separate the integrals. I cannot solve it in one integral, right? Because dl gonna be different. Also, I already know that I also can be different. So it's a given thing. Okay, good. So this is for 1, this is for 2, right? And be careful, it's the opposite around here, right? The opposite way. Good. By the way, what's going to be the contribution of that DL?
0.
To here, the magnetic field? This wire and this wire? 0. Why 0?
Because it's the same direction.
Exactly. I already see, look, your RDB, right, the distance is from the source to the point, which is going to be at, let's call it the x direction, right? The x direction, good. And for it, it's going to be the minus x direction. But DL is also going to point in the radial direction. So this is dying out, okay? So I don't care about these terms. I only care about the circle. Good. Really good. Okay. So we understand these terms, which is really good. But we're still missing one, which is, what is the current, right? Usually, this would not be the challenge in this kind of question. The challenge is going to be this, okay? But this is, I only give hard question in this time of the semester, right? So we need to figure out what is this, okay? So what this could be, for each one of them, I'm going to do the question more easy. We want something to find, way to find what is I1 and I2 for each one of them. How I can find them? What I know, do I know any relationship between them?
It feels like they should be equal.
The what?
It feels like they should be equal.
They should be equal. Why? I didn't tell you, but you have here a resistance R1, and this one have a resistance R2. Okay? Thank you. Okay? So, should they be the same? Here, maybe R1 is bigger than R2, and all the charges would see, oh fuck, I don't want to enter that. This is a high resistance. I prefer to go that way, okay? And only the electron that fucked up gonna go that direction, right? So we're gonna have some split here, okay? So, but what we do know, what's happening in this point? Exactly. This means that charges are not accumulated, okay? Okay, Kirchhoff's law is just saying charge is not accumulated, which is not hold for capacitors. Remember, capacitor actually accumulate charge. In this point, what enter is the same as what leaves, okay? That's the idea. So I know already the 2I actually equal to I1 plus I2. Great, great, one equation. What is another equation that I can use? I'm gonna give you a hint.
Ohm law?
Exactly. What I see here is I see that these two resistors actually being held by the same 2 points. For example, if this is a hill and this is a valley, so the two of them have the same potential drop. Okay? So the encouragement to go to that point in a more perspective of energy is the same, right? This is the mountain, this is the valley, current going that direction, right? Maybe here it's going to be harder, yeah? But the potential energy is the same. So I also know that V1 is also equal to V2, right? I also know that because they are connected in parallel, right? Good. So this is I1 multiplied by R1 equal to I2 multiplied by R2, right? Good. And what we're actually doing right now is we're starting to talk about the component, about the circuit, okay? So when we compare them, so we can actually make this simpler, and we see that I1 is actually the ratio R2 divided by R1 multiplied by I2, right? So we know the ratios, good. And using this equation also, we have 2 equations and 2 unknowns, right? So we can find from that this thing. Using these 2, we can find that I2 equal to 2I. This gives me the units of the current, and now correction factor, which is R1 divided by the sum of them. And for I1, it's the other one. It's 2I multiplied by R1 plus R2, and here I'm going to put R2. Okay? We found the currents. we found RDB, we found DL, we got everything we need to find the magnetic field. Good? Let's find it. Okay, so this is working, not working. Okay, so let's do it. So I'm going to clean it here, because I want you to still see these terms. So the magnetic field in the center, right, at 0, 0, is equal to the sum of all the small contribution that available to me. We said already that this one are 0, right? This is the straight lines. They're going to cancel out. But we have this wire, right, that's going to contribute. What I need to put here, first of all, I need to put this constant, right? KB. Then I need to put the current. Which current for that? I1, which I already found. It's a really big term. Let's put it as I1. Yeah, I1. Then I need to put what? DL. Which one? Exactly. So I need to put A d theta minus theta. Why? Because I'm going in the current in that direction. Don't fall. It's an American question like. So minuses could be a problem. Okay, you have a lot of advantage when you have this kind of exam, because you can pick at the solution and understand. Okay, maybe this looks similar to that, and understand what's going on. And if you succeed, you already know that you succeed because you have the option. But don't fall on the minuses. Okay, it's really important. Good. So we have this cross what? A minus R, right? And here it's really easy, it's A squared, right? Cool. Now we have, and what the integral is about. Now I can see what I actually summing is theta. So I'm going to start from angle, what? 0 till angle, whoop, pi. Got it? Good. So, but I did not finish. What I do have? Another wire, right? So this wire is actually the integral, right, which is going to be really similar to it. KB I2 AD theta, in what direction? Now it's the plus sign, because I'm going at that side, I'm going with the rising of theta. Okay, plus. Good. Divided by the same A square. I forgot the cross. And I have cross of the same. A minus R. We are good? That's the integral. Let's solve it quickly and move to the next question. Okay? So I can do some tricks. KB, I can take it out, right? A cancel out here, cancel out here. What is the boundaries of this integral? The same, 0 till pi? From pi to, exactly, pi to 2 pi. Okay, be careful about that. Okay? Good. KB is out. I can also take the currents out. You see it? Because they are the same beside, cameraman? They are the same, the currents are the same beside this term, right? The resistance on top. But look, it's the other way around, right? So it's KB. I can put here I can put it 2I divided by R1 plus R2. This is the time to look at the solution and look for R1 plus R2. Okay? I'm in the right direction. Okay? It's important. Use it. Good. We still have this A right here. Good. And we have this R2, right? Integral d theta 0. Also this A cancel, right? With this, right? No, this was magnitude of 1. Remember, it was hat. You see here? Hat? So it's 1, okay? The unit did not make sense to me. Now I understand why. Okay, good. So this is 1, not cancelled. It's still here. 0 pi plus we need to do this cross. What this cross going to give us? I'm going to remind you, R theta z, right? So this is theta cross r. Theta cross r give a z, and the minus minus cancel each other. Right? Theta r minus z, correct? So this is going to be minus z. Good. And here we're going to have r1 integral d theta pi till 2 pi, right? And this is theta r z minus z, but we have here a minus, so plus. And this is really good because it's going with my intuition, right? If I'm gonna try to see what is the contribution using the right hand rule, I'm gonna see that all of this is gonna contribute in that manner, right? X. But this actually gonna contribute this. So you say, okay, great, I'm on the right path. Okay, you see it? This compared to this. You see it? Yes.
We need to do the cross product, or we can just use the right hand rule?
It's the same thing. Doing the cross product and do the right hand. In order to delete the cross, you have a few ways to do it. Determinate, right? Or right hand rule, whatever you like. Okay? Good. So this is gonna give us pi, right? This is gonna give us also pi, right? But with the minus. Good. And the solution is the final one. It's gonna be it's gonna be KB, the constant, divided by A, R1 plus R2, 2I. Here I have R1 minus R2, right? The pi get outside, right? And we have this one minus that. You see it? And now you need to look at the solution and see, I love this KB because it's less to write, right? Instead of mu 0 divided by 4 pi, but sometimes you need to write them all. So in our case, you actually needed to write them. So pi die out, this die with that, 2, and you just need to multiply by mu 0 divided by 2. Okay? So this is the question. I think it's a really good question for two reasons. Why? First thing, it's talking about biu-Savart, okay, which is a really hard subject, in my opinion. I think the hardest is biu-Savart, okay? And then, you need to see that you understand what's going on in a circuit, okay? You have the same potential drop, same 2 points, and need to understand that you have conservation of charge, okay? There's no accumulation of charge. Whatever come, whatever go, okay? Kirchhoff's law, also known. Good. And what I want to tell you is that, okay, that is actually the good case, okay, the bad case. Usually don't want to do these ways, but sometimes you are lucky. Sometimes there is symmetry, infinite symmetry. If you have infinite symmetry, okay, you're not going to use that. Okay, you're going to use Ampere's law, right? What Ampere's law said? He said B dot dl equal to mu 0 I penetrate. And if you have a symmetry, you're going to use here Gauss's law, okay? dA equal Q in divided by epsilon naught, okay? So every time you have a question, okay? Every time somebody asks you a question about find a field, if it's magnetic, you look at this column, okay? You said, okay, this or this. You have infinite symmetry or circular or something like that. You said, okay, I can probably can use that thing, okay? And if you don't, and if they talk about electric field, okay, I'm going to use Gauss's law. And I want you to notice that we have the same concept. You see it? It's the same idea. Okay, it's the same concept. I'm not going to do right now question regards to that. You have many, but you should practice them. Okay, that's the concept. Okay, I only did that. We are short in time. Okay, good. That's great. And I want to remind you that Q in every of this location could be it could be divided on a straight line, right? Not straight line, but on a line, on a loop. It could be divided on an area, okay? which is hold for conductors most of the time, and it can also be on a volume, right? And the current can actually be right as JDA, right? So you need to be careful on that. Also less familiar, but it could be also the J is equal to V multiplied by rho. Rho also can charge density. You gave the charge velocity, boom, you got some charge flux, okay? That also can happen, okay? So good, we talked about that, that's really good. And what we actually cover here is the basics, is how charge behaving according to fields. And if we're gonna use these concepts, we can actually build devices, capacitor, inductor, resistor, okay? So let's do that. So let's talk about that a little bit. So אוקיי. אתה יכול להרים את זה? תודה. תניח את זה פה לזה. תיקח אותו אחר כך. So right now I want to give you another summary that I did, which is talking about the second part of the course, which is actually the components. Okay? So if we want to accumulate electric field, we're going to use what's called capacitor. Okay? Where does capacitor actually come from? If you have some voltage, okay, and you put it across some device with some geometry, okay, you're going to use Gauss's law, because that's going to be a really nice geometry. Okay, Gauss's law, and then you're going to get from Gauss's law a charge, right? All this journey is actually capacitance. That's the idea. What is the formula for capacitance? Q, right? Q equal CV, right? This is the concept of a capacitance, okay? And you need to know some basic capacitors, okay? For example, you need to know that for a plate capacitor, right, C is equal to epsilon A divided by D. You need to know for a cylinder, it's 2 pi epsilon L divided by ln R out divided by R in. This is the more familiar ones, but you also have this concept in the magnetic world. What we have in the magnetic, we don't care about voltage, we care about current. Not about charge, about current, okay? And charge produce electric field. Charge actually produce magnetic field. We can use Ampere law, why? Right? And then we can find the flux, phi b. And all this is actually L. This is, and we have the equation phi b equal I L, right? This is the concept of that, okay? That's the idea. Every time you have L, somebody did this direction, okay? He found the magnetic field, he used Ampere law, okay? And then found this flux. Okay, good. So we have that. Familiar one that you need to know, solenoid, right, is actually mu naught n squared A divided by I. Okay, good. And if I want to jump in this direction, what actually jump from current to voltage? This is Ohm's law, right? So if I want to do this jump, it's actually multiplied by R. Right? So this is the component that we have. We have the one that can accumulate charge, capacitor. We have the one that can accumulate current or magnetic field, call it however you like. And you have the one that actually want to get rid of all the energy, the resistors. This is the cycle. Got it? Okay, good. I want to cover that. Good, okay. So next question I want to do is is to start to talk, when we talked about the relationship between them, okay, we are actually getting to the last part of the class before waves. Wave is actually separate part of the class, but the last part of electromagnetism is actually the circuit component, okay? So the last part, the circuit component, is actually talking what happens when I actually start to mix this one with each other. For example, I can have RC circuit, right? And I can have RL circuit, and I can have LC circuit, and I can have RLC circuit, okay? So we didn't cover in the tutorial the LC circuit, and I want to do it with you right now, okay? So I found a question regards that. Here it is. Good. You know what? Let's do the hard one. Let's do that. Okay, it's harder question. Okay? Okay. If you can pause and start the video, it's going to be great.